रहीम अस्सलाम वालेकुम दोस्तों, क्या हाल हैं? कैसे हैं आप सब लोग? उम्मीद करता हूँ खैरियत से होंगे। दोस्तों, आज की इस वीडियो में हम डिस्कस करेंगे काइनेटिक्स ऑफ होमोजेनियस रिएक्शंस। सिंपल रिएक्टर टाइप्स। Ideal reactor have three ideal flow or contacting patterns. We shows these in figure 2.1 we very often try to make real reactor approaches these ideal as closely as possible. We particularly like these three flows or reacting patterns because they are easy to treat. It is simple to find their performance equation, and because one of them often is the best pattern possible, it will give the most of whatever it is we want. Later we will consider recycle reactors, stacked reactors, and other flow pattern combination, as well as deviation of real reactor from these ideals. The rate equation. Suppose a single phase reaction AB plus BB gives us RS plus SS. The most useful measure of reaction rate for reactant A is then rate of reaction is equal to rate of disappearance of A multiplied by divided by the minus sign means disappearance 1 over V is equal to T, and A over dt is equal to amount of A disappearing over volume multiplied by time. Its unit is mole per meter cube second. In addition, the rate of reaction of all materials are related by minus R over A is equal to minus R over B is equal to R over R is equal to RS divided by S. Experience shows that the rate of reaction is influenced by the composition and the energy of the material. By energy, we mean the temperature, random kinetic energy of the molecules, the light intensity within the system. This may affect batch reactor. Steady state flow means includes plug flow reactor and mixed flow reactor, batch reactor. Uniform composition everywhere in the reactor, but the composition changes with the time. Plug flow reactor fluid plug flow reactor find fluid passes through the reactor with no mixing of earlier and later entering fluid and with no overtaking. It is as if the fluid moves in single file through the reactor. Mixed flow uniformly mixed the same composition everywhere within the reactor and at the axis. Ideal reactor type. The bond energy between atoms, the magnetic field density, etc. Ordinarily, we only need to consider the temperature, so let us focus on this factor. First, we can write rate minus R capital A mole per meter cube second is equal to temperature dependent terms, concentration dependent terms. Here are a few words about the concentration dependent and the temperature dependent terms of the rate. Concentration dependent terms of a rate equation. Before we can find the form of the concentration term in a rate expression, we must distinguish between different types of reactions. This distinction is based on the form and number of kinetic equations used to describe the progress of reaction. Also, since we are concerned with the concentration dependent terms of the equation, we hold the temperature of the system constant. Single and multiple reaction. First of all, when material react to form product, it is usually easy to decide after examining the stoichiometry, preferably at more than one temperature, whether we should consider a single reaction or when a single stoichiometric equation and single rate equation are chosen to represent. We have a single reaction when more than one stoichiometric equation is chosen to represent the observed changes. Then more than one kinetic expression is needed to follow the changing composition of all reaction components, and we have multiple reactions. Multiple reaction may be classified as series reaction. A gives us R gives us S. Parallel flow reaction, elementary and non-elementary reaction. Consider a single reaction with stoichiometric equation A plus B gives us R. If we postulate that the rate controlling mechanism involves the collision or interaction of single molecules of A with a single molecule of B, the number of collisions of molecules A with B is proportional to the rate of reaction. But at a given temperature, the number of collisions is proportional to the concentration of reactants in the mixture. Hence, the rate of disappearance of A is given by rate minus R is equal to KCA capital and CB. Such reactions in which the rate equation corresponds to stoichiometric equation are called elementary reactions. When there is no direct correspondence between stoichiometric and rate, then we have non-elementary reactions. The classical example of non-elementary reaction is that between hydrogen and bromine. I2 plus Br together to HBr, which has a rate expression or HBr. Non-elementary reaction are explained by assuming that what we observe as a single reaction is in reality the overall effect of sequence of elementary reactions. The reason for observing only a single reaction rather than two or non-elementary reaction is that the amount of intermediates formed is negligibly small and therefore respect detection. We take up example explanation later.